Okay, so it looks like this is not factorable. So the other option is to use the quadratic formula. So x equals minus b plus or minus the square root of a squared minus 4ac, or b squared minus 4ac, so that's 16 minus 4 times 3 times minus 8 all over 2 times 3, 2 times a. Okay, so if you work this out, you end up with 2/3 minus square root 7 over 3 and 2/3 plus square root 7 over 3. Okay, so let's get the approximate values of these. So the first one is approximately negative 1.9, or rather negative 1.097 it looks like. And the second value is approximately 2.4305. Now remember that the interval we're working on, we're looking at f on the interval negative 2 comma 4. Okay? And it looks like both of these numbers are in the interval. So there are two locations where f prime is equal to 0. So there's a c1, which is 2/3 minus square root 7 over 3, and c2, which is 2/3 plus square root 7 over 3. So there we go. We found the values that are guaranteed by the mean value theorem. I'm sorry, by Rolle's theorem. Now, the next thing we're going to do is we're going to look at the mean value theorem. Okay? Now, the mean value theorem is kind of similar to Rolle's theorem. It has less requirements, and for that reason it's a little bit stronger, but it's very closely related to it. So let's write it down. The mean value theorem. Okay. So f is a function on the closed interval AB. So the mean value theorem has two requirements. One, that f is continuous on the whole interval, the closed interval, so everywhere inside as well as the endpoints. And number two, f is differentiable everywhere. On the open interval AB. So that's it. It's the first two conditions of Rolle's theorem. There's no third condition. Okay? Then there is a guarantee about f prime. But before we write that guarantee, let's see if we could make sense of it from a diagram. So here's f of a. And here's f of b. So they don't have to be equal. But then the function can do whatever it wants, as long as it is differentiable everywhere and it's continuous on the closed interval. Now I'm going to draw a secant line that connects the endpoints. So let's draw a secant line here. And then notice that there is a very special place I think it's here. So there is a special point here. And let me trace that point down here. There is a point here. That's a tangent line. And the green one is a secant line. And these are parallel. That you can always do this is what the mean value theorem says. So there is a location on the graph where, so here now we're ready to write down the statement. where the slope of the tangent line, so that's f prime of c, is equal to the slope of the secant line, f of b minus f of a over b minus a. That's just the slope formula, y2 minus y1 over x2 minus x1, okay? And this is guaranteed for at least one number c in the open interval AB, that you can always do this. So what is the interpretation of this? Let's see. The interpretation of this is that what we're saying is the instantaneous rate of change is equal to the average rate of change at some moment in time. So instantaneous rate at some moment in time is equal to the average rate of change. So let's take a look at what this means in terms of velocity. So for example, if f of t is the position, okay, and let's say you travel 100 miles in 2 hours, okay, that means your average velocity is 50 miles per hour. Now it doesn't mean that your speedometer is always showing 50 miles per hour throughout the 2-hour trip. At some point you travel faster than 50, at some point you travel more than or less than 50, slower than 50. But what the mean value theorem says, at some point in time within the 2 hours, your speedometer is exactly showing 50 miles per hour. That is what the mean value theorem says.